Hello, today we will talk about the cavity theory. I will introduce this concept, the cavity theory. So, cavity theory, this theory is used to find a relationship between the dose deposited in the cavity to that in the surrounding medium. So, when I say cavity, what does it mean cavity؟ شو يعني cavity؟ شو هي الكافيتي؟ Here we can talk about the dosimeters. So dosimeter من اسمه يعني it's a tool, an instrument used to measure the absorbed dose at a specific point in the medium. So it's a radiation sensitive device. It's a radiation sensitive device, a device which is sensitive to radiations. When the radiations enter a specific medium, when the radiations enter the body, let's say, these radiations could be detected and could be sensed using a dosimeter. So the sensitive medium of this dosimeter is called the cavity. So a cavity is the internal part of a dosimeter, sensitive part, sensitive medium of the dosimeter. Now, the cavity theory, or in general, the sensitive volume of the dosimeter is in general not made of the same material as the medium. It is not made of the same material as the medium. Here we have, as you see in the figure, we have a medium, and here we have the dosimeter. Inside the dosimeter, we have the cavity. So the medium inside the dosimeter differs to that of the surrounding medium. So we need, when we introduce cavity theory, what we need is to find this relationship between the dose deposited in the cavity to that deposited in the surrounding medium. أكيد surrounding medium والcavity بيفرقوا عن بعض. They differ in atomic number, in composition. لهيك في عندي different deposit أو في عندي difference when we compare the dose deposited in the cavity to that deposited in the surrounding medium. The main interest of the cavity theory are to study the modifications of charge and radiation distribution produced in the medium by the cavity. This is the main interest. Also to establish this relationship between the dose in the sensitive medium and the sensitive volume of the dosimeter and the dose in the medium, in the surrounding environment. هيدا الهدف من الكافيتي ثيوري. هلا اكيد نحن هنشتغل وهنركز على الراديشنز بمعنى a beam of photon for example. يعني لما نحكي عن الاكس راي مثلا، الاكس راي هو عباره عن photon particles. في عندنا photons، هدول الفوتونز will interact with the internal medium, with the internal environment, with the body, with the tissues, with the organs. وأكيد this interaction is complicated. We need to study this interaction. We need to measure the absorbed dose, for example. We need to sense this interactive the interaction between the radiations, the photons, and the medium. We need to obtain information about that. So cavity theory relate the detector signal to a dose in the surrounding medium. For many years, the cavity ionization chambers have been the preferred detectors to measure the absorbed dose from ionizing radiation. كان هلا في عندي انواع حنتعرف عليهم بعدين. مثلا اذا بدي احكي عن دوزيميتر او بدي احكي عن كافيتي معينه، واحده من الانواع يلي كانوا يستعملوها بشكل كتير كبير الايونايزيشن تشامبر. ionization chamber, cavity ionization chamber. فاذا بهيدي التشامبر بده يصير في انتراكشن. هيدا الشيء لازم ندرسه ونعرف النتيجة، نتعرف على النتيجة أو نحصل على معلومات عن الراديشن عن طريق هيدي التشامبر أو عن طريق هيدي الكافيتي. So cavity theory formalisms relate the detector signal to a dose in the surrounding medium. The common cavity theories are straightforward to calculate, but make limiting assumptions about the charged particle fluences in the chamber and in the medium. فإذا الكافيتي ثيوري، بس نحكي عن كافيتي ثيوري بنحكي عن كافيتي ثيوري بالدوزيمتري بالدوزيمترز. So it provides a framework for relating the radiation energy absorbed in a detector in a cavity to the absorbed dose in the surrounding medium. This theory is important and essential to calibrate radiation detectors, also to understand how those measurements in small volumes in small detectors correspond to those in larger materials or tissues. فإذا الكافيتي as you see in the figure هي عبارة عن small region within a larger medium. It represents a radiation detector. هنا يعبر عنها ب ionization chamber مثلا. أعطي example ionization chamber أو calorimeter أو أي other cavity, other type of cavities. So it represents, so the cavity represents a radiation detector embedded in a material like tissue, like water, like air, and other medium. Now we have different types of cavities. First of all, let's see these types. So a cavity can be either small or intermediate or large in size. إذا هذا الشيء قادرين نشوفه بالصورة. We can assume that the cavity is small or intermediate or large in size compared to the range of the charged particles in the cavity. هلا في عندي كذا theory. مثلا Bragg-Gray theory. This theory deals with small cavities. And we have other theories that deal with intermediate cavities or with large cavities. فإذا كconcept إذا بدنا نحكي عن Bragg-Gray cavity theory, it assumes the cavity is small enough that it doesn't disturb the charged particle fluence. The dose in the cavity is due to charged particles produced in the surrounding medium that pass through the cavity. Then we have different assumptions. كان different assumptions. نحكي مثلا عن the first assumption states that the dimensions of the cavity are much smaller than the range of the charged particles within it. So this ensures that the presence of the cavity doesn't significantly alter the distribution of charged particles inside it. In other words, the charged particles' trajectories are minimally perturbed by the presence of the cavity, allowing for simpler calculations. So the cavity dimensions are so small when compared to the range of charged particles within it, so that the fluence of charged particles inside the cavity is not perturbed by the presence of the cavity. We have another assumption اللي هو إنه there are no interactions of uncharged particles in the cavity. So no interactions of uncharged particles in the cavity, so that the absorbed dose deposited in the cavity is due to the charged particles that cross the cavity. So this assumption, no interactions of uncharged particles, this assumption states that there are no interactions involving uncharged particles مثل الphotons والneutrons within the cavity. As a result, the absorbed dose deposited within the cavity is solely attributed to the charged particles that pass through it. So this simplification allows for a clearer focus on the contributions of charged particles to the absorbed dose within the cavity, without the complexity introduced by interactions involving uncharged particles. فإذا هيدا المين assumptions، هدول المين assumptions. يعني أول شيء عندي small cavity dimensions، ثاني شيء عندي no interactions of uncharged particles. فإذا cavity بتكون small مقارنة مع range of the charged particles within the medium. The fluence and their energy spectrum inside the cavity remain undisturbed by the cavity's presence. بالنسبة لتاني assumption, the energy deposition in the cavity is entirely due to the charged particles that pass through the cavity. فإذا the uncharged particles do not interact within the cavity and therefore do not contribute to the dose directly. فإذا كequation, here we can see the Bragg-Gray equation. It relates the absorbed dose in the cavity اللي هي dg to the absorbed dose in the medium اللي هي سميناها هون dw. So dw هي absorbed dose in the medium w, dg is the absorbed dose in the cavity g. So the Bragg-Gray equation relates this absorbed dose in the cavity to the absorbed dose in the medium. I can say that dw equal dg times s g. شو هي الاس؟ هيدا السيمبل يلي شايفينه هون. It has also a double bar. في عندي s double bar. This double bar is to indicate that this ratio of average stopping powers. يعني هون في عندي الاس بيعبر عن average عن ratio of the average mass stopping powers of the medium and the cavity gas. بيعبر عن ratio معين. بيعبر عن ratio. So here in the equation d phi over dt هي the fluence energy distribution of the electrons in the medium. So now another cavity theory. فإذا هيدا بالنسبة للبراغ-Gray cavity theory. فإذا بالنسبة لهذا الموضوع فإذا هو مرتبط ب different assumptions. يعني different assumptions لازم ناخدهم بعين الاعتبار. من ضمنهم إنه في عنا cavity with small وفي عنا small cavity with small size. وكمان الcavity dose in the cavity is due to charged particles only. Okay, so no interaction of uncharged particles. الإيكويشن شفناها هون. فإذا الأس برجع بعيد هي ratio. Okay, ratio of average stopping powers. So stopping power of the material للميديوم أو للكافيتي. طيب another cavity theory. في cavity theory كتير كمان معروف وفينا نحكي عنه هو الفانو theorem. The Fano theorem. So فإذا البراغ-Gray theory is a method to measure the absorbed dose in radiation dosimetry. It involves placing a small cavity in the path of radiation. Okay? Now, concerning the Fano theorem, so it is proved by Ugo Fano. هذا اسم الساينتست. It is proved by Ugo Fano in 1954. So Fano addresses the behavior of secondary radiation in a medium exposed to a uniform field of primary radiation. So this theorem states that the field of secondary radiation is also uniform and independent of the density of the medium, as well as of density variations from point to point. This theorem is also important because it implies that even in situations where the density of the medium varies, the behavior of secondary radiation remains consistent. The conditions required by the Bragg-Gray theory are better accomplished if the composition or atomic number of the cavity is similar to that of the medium. This was observed in experiments with cavities filled with different gas compositions. And in 1954, Fano proved the theorem. شو بيقول الثيورم in a medium of given composition exposed to a uniform field of primary radiation, the field of secondary radiation is also uniform and independent of the density of the medium as well as of the density variations from point to point. فإذا شو أهمية هيدا الفانو theorem? So it is important because it relaxes the requirements on the size of the cavity used in dosimetry measurements. So it relaxes the requirements on the size of the cavity used in dosimetry measurements. It's often challenging to meet the condition of having a cavity much smaller than the range of charged particles, especially when dealing with low energy photon beams. So the Fano theorem's applicability helps make those measurements more feasible in various scenarios, in different scenarios, even when the cavity dimensions are not perfectly small compared to particle ranges. فإذا this theorem is valid only for infinite media and in conditions where the stopping power is independent of density. فإذا الفانو theorem يعني this theorem refines the Bragg-Gray theory by considering the spectral distribution of secondary electrons and their energy loss processes within the cavity and the surrounding medium. So it takes into account the fact that the stopping power of a material depends on the energy of the incident particles. Now, other cavity sizes. We have other cavity sizes, of course. We can talk about different cavity sizes. The relationship between the dose to the material, dW, surrounding the cavity, and the dose to the medium, dm, where the cavity is immersed, this relationship is expressed as dm over dw. Here, so dm is the dose to the medium where the cavity is immersed, dw is the dose to the material. We talk about the cavity material. So هيدا الريشيو شو بيساوي؟ ميو اي ان over rho للm, so mass energy absorption coefficient of the medium over the mass energy absorption coefficient of the cavity material. So this relationship is valid under the following three conditions. Our condition, so these conditions are implicit. Our condition, there is CPE in material. There is charged particle equilibrium in material W and in medium M. So there is CPE in both the surrounding medium, the surrounding material, and the medium itself. This means that the energy transferred to the charged particles by the photon beam is entirely deposited locally without any net flow of particles in or out. So we have an equilibrium. Any condition, the photon beam is monoenergetic. So the incident photon beam has a single energy level. This is a second condition. This simplifies the interaction processes and ensures a consistent photon fluence and interaction rate. ثالث condition, the photon fluence is the same for both media. So الفوتون fluence برجع بذكر انه الفوتون fluence هو number of photons crossing a unit area per unit time. So photon fluence is the same for both materials. The W will M. If the elemental compositions of W and M is not similar, the backscattering of photons at the boundary can change significantly the photon fluence, regardless of the dimensions of W. This is a note that should be considered. فإذا accuracy of dm over dw relationship depends on maintaining these conditions. Now, when the photon beam has a spectrum of energies, instead of being monoenergetic, those relationship between dm and dw is expressed using an energy weighted average of the mass energy absorption coefficients, as it's given by this equation. dm over dw equal this equation. يعني فيني أعبر عنها هالمرة dm over dw equal mu en over rho bar. So هنحكي عن energy weighted average of the mass energy absorption coefficient. So هي average ratio of mass absorption energy coefficient, which takes into account the photon spectrum that irradiates equally both materials, considered a large cavity. And also that takes into account M, the material. Another cavity is the Burlin cavity theory. In 1966, Burlin proposed an intermediate cavity theory. يعني هون صرنا نحكي بcavity which has this cavity has intermediate sizes. So it describes the situation when the ranges of electrons were comparable to the size of the cavity. هنحكي عن intermediate cavity عن intermediate size. So هذا بالبيرلين theory. فإذا also the cavity and medium are in CPE. Third point, we have elemental compositions of both. The elemental compositions of both medium and cavity are similar. فإذا كمان البرلين theory extends the Bragg-Gray cavity theory to cavities of intermediate sizes. In this theory, a relationship between those in the cavity with those in the surrounding medium takes into account the effects of cavity size on the charged particle equilibrium and the interactions between the cavity and the medium. فإذا both the cavity and the medium are assumed to be in charged particle equilibrium, meaning that the energy deposited by the secondary charged particles in the cavity and the surrounding medium is balanced. كمان بنحكي عن similar elemental compositions. يعني elemental compositions of the cavity and the surrounding medium are similar. كمان هيدا الاسامبشن كتير مهم. Because differences in composition would cause variations in the photon fluence and secondary particle interactions at the cavity boundary. فإذا هون بهيدا الثيوري Burlin theory, cavity size is not negligible. It is intermediate. يعني شو يعني intermediate؟ يعني cavity dimensions are large enough to perturb the fluence of secondary charged particles, but not so large that they affect the equilibrium significantly. هلا فينا نشوف هيدي الايكويشن بالبيرلين كافيتي ثيوري دي جي اوفر دي دبليو. كمان هيدا الريشيو شو بيساوي؟ It depends on D. في عنا بارامتر دي هون D describes the ratio of the cavity size and the range of the secondary charged particles. It influences the relationship between the dose in the cavity and the dose in the surrounding medium. فإذا parameter D assumes values between 0 and 1 according to the cavity dimension. We use D equal 1 for small cavities and D equal 0 for large cavities. يعني D بتاخد بعين الاعتبار الcavity dimension. This is concerning the cavity theory and the different types of theories available.